Hello everyone. Thank you for joining another video session of thermodynamics. Today, I'm going to explain the Clausius inequality. Clausius inequality. Clausius inequality. Now, to discuss about Clausius inequality, we need to have a little bit of background in thermodynamics cycles. A thermodynamic cycle is defined as a sequence of thermodynamic processes that starts and ends at the same state. So we can schematically draw a thermodynamic cycle by schematically drawing a system which is at a one equilibrium state. Let's number that state as state 1. And due to a heat interaction or work interaction or both, or maybe mass interaction, that equilibrium state of the system changes to another equilibrium state, which is numbered as 2. So this process, this is a thermodynamic process, is called process 1 to 2. Now to complete the cycle, we can always come back to the initial state from state 2 to 1. That also completes the smallest cycle in thermodynamics. But I would like to add another state for the sake of clarity. Let's number that as state 3. And now this comes from state 2 to 3, process 2 to 3. And also it returns by completing the cycle, process 3 to 1. Now, Clausius looked at those cycles because cycles were important at that late 1800s due to industrial revolutions. Look at those cycles and quantify this quantity delta Q over T. Delta Q here is the infinitesimal amount of heat transfer, and T is the temperature of the boundary at the time of that heat transfer. So during a process, there could be a finite amount of heat transfer to its surroundings, and this temperature and amount of heat transfer could change time to time. And if you want to find the entire quantity or the summation of this quantity during the process, we can do it by integrating that from state 1 to 2. That gives you the amount of change in this quantity delta Q over 2, delta Q over T for that particular process. And we can find the same total quantity for the of the same quantity during the process 2 to 3 and 3 to 1 and add up to this 2 to 3 delta Q over T plus 3 to 1 delta Q over T. And then Clausius figured out no matter what cycle he does this and no matter what processes that involve in here, this quantity always adds up less than or equal to 0. Then he came up with a concise mathematical expression by using this cyclic integration, which actually denotes it's close around the cycle, delta Q over T less than or equal to 0. And this is named after him and says that Clausius inequality. Now, as soon as we see this, we have a question, okay, when does this quantity or cyclic integration of delta Q over T equal to 0? Now, later found that for internally reversible processes or total reversible processes, if the cycle is made up of internal reversible processes, this quantity delta Q over T equal to 0 for the cycle which made up of internally reversible processes. If any of those processes in a cycle is not internally reversible, then it is less than or equal to 0. Now every process has in a cycle has to be an internal reversible process for this to be equal to 0. This inequality equal to 0. Okay. Now there's no internal reversible process in reality, but it is an ideologically you can say that this quantity is equal to 0 when all the processes are internally reversible. Then later found that this quantity delta Q over T has characteristics of properties. That means this quantity of a system does only depend on the state of the system. Now let's say at state 1 this delta Q over T is 5, and no matter what process that you um, no matter what process that is taken place when the system transfers from state 1 to state 2, as long as the two states are identical, the quantity at two different states remains the same. Okay, again, if delta Q over T equals 5 at state 1 and delta Q over T is 10 equal to 10 at state 2, it doesn't matter how the system transfer from state 1 to state 2, the quantities at each state has the same values as before. Okay, so this is a state dependent. Unlike work co-heat, which are path dependent, this is a property, and this property is named entropy and denoted by S. And then for internal reversible processes, the infinitesimal change in entropy is equal to infinitesimal change in heat transfer divided by T for internal reversible processes. If one want to find the change in entropy during a process, what we can do is we can take the integration in both sides, right? And we can say this delta S is equal to S2 minus S1, right? That is equal to 1 to 2 dq over T. But this process has to be internally reversible. Okay. Now, well, you can say that, okay, if you know T in terms of a function of Q, we would be able to find this S2 minus S1 for an internal reversible process. But it's not always easy. In particular situations like internally reversible isothermal process, for an internal reversible isothermal process, since it is internal reversible, we can write delta S, which is equal to S2 minus S1 equal to 1 to 2 isothermal process dq over T. T is a constant here. Let's say T naught internal reversible. Now, since T naught is a constant, you can take it out from the integral, and 1 to 2, right, dq for an internal reversible process. So this is this quantity right here, this quantity right here, is the total heat transfer during that process. So therefore, for internal reversible isothermal process, delta S is equal to S2 minus S1 equal to Q1 to 2 over T naught. So we can come to that conclusion for an internal reversible process, internal reversible isothermal process. If the heat transfer during the internal reversible isothermal process is known, we can readily calculate the total entropy transfer or total entropy change during the process. Okay, so today in this video we learned that thermodynamic cycles involving thermodynamic cycles, there's a quantity delta Q over T which cyclic integration is less than or equal to 0, which is known as the Clausius inequality. And Clausius inequality becomes 0 or holds equality when all the processes are internal reversible. And for an internal reversible process, we can calculate the total amount of entropy change by using the integration of delta dq over t. And also for an isothermal process, if the total amount of heat transfer during the process is known, we can find the total entropy change based on Q, total amount of heat transfer divided by the isothermal constant temperature of the system during that process. So that's it for this short video. See you in another. Thank you very much.